Okay, welcome back to part 2 of our periodic table notes. So part 1, if I could summarize, was really a lot of review of things we had done in the previous unit on atomic structure. So just reinforcing what's in an atom, where are those things located. We did add a little bit more information about some different parts of the periodic table, like the metals, the metalloids, and the nonmetals. So now you should be able to describe those a little bit and know which kind of element is which one. So we're going to drill down a little bit more into some other things we can see on the periodic table. And I want to teach you a different way to represent atoms. It's much simpler than some of the ways we've been using already. Okay, so we've been drawing these models called Bohr models, right? And some of the atoms that you see down here are that example. But there's a better way, a simpler way. And it shows the most important electrons in an atom. Because it turns out what atoms do really depends mostly on their valence electrons. Those are what I call the most important ones. And just to remind you, valence electrons is another way of saying the outer electrons. As always, make sure you're listening to what I'm saying, not just watching the closed caption. And if I say things too fast, or if I write too fast, you can pause it or stop it and get caught back up. So just to remind you that all the electrons are living in these things called energy levels, like here. So the pictures that I've shown here, these models all have two energy levels outside the nucleus. These big things here represent the nucleus. And so those outermost ones in the second energy level would be considered the valence electrons. Most atoms have a lot more than two, but I've kept this kind of simple. All right. So this model is going to show you only the outermost electrons. It is known as a Lewis dot model. The name Lewis, just the person who kind of came up with this idea. So much easier. I'll remind you when we did the lab in the last unit, remember these pictures? These were the Bohr models. And oh my heavens, how hard it was to like see everything in there. But remember what I had you do on this lab was just to draw in the outermost electrons, because those are the important ones. So I wanted you to see the connection between the column number and those outer electrons. So what we're going to do now is we're going to represent everything in the atom, the nucleus, and all of the inner levels with just the symbols of the element. Okay, so this first one here, notice we've got 5 electrons represented, 2 in the first level, 3 in the second level. And so element number 5 on our periodic table must be boron. So what we do is we just use the letter B to represent all the stuff except the outer electrons. And then we put dots on it just to represent the outermost ones. So because boron has 3 in the outer level, we'll put 3 dots on it. Now, it really doesn't matter. When I was taught to do this, we were taught to put the first 2 on the right, and then we put the other ones around it, kind of left, right, top, bottom. But as long as you got 3 there, I'm not going to really worry too much where they go. We do like to put them left, right, up, down. Don't put them like this picture here, where like a triangle form. That would look kind of weird. Okay. And what about this one here? It's got 6 total electrons, so it's the one next to it. This is carbon. So we would use the letter C, and then we would draw 4 electrons around it. Now again, I don't really care where they go. I learned to first put the first 2 on the right, and then I put 1 on the top, 1 on the left. Don't worry about where they go, just put 4 on there. And then moving on, you see we're just adding 1 electron each time, so this next one is going to be nitrogen. Nitrogen is N. And then we're going to have 5 electrons around it. So I'll put 2 on the right and then 1 on the other 3 sides for a total of 5. And the next element over is oxygen. Oxygen is going to have 2. And then because we have to fit 6, we're going to have another side that has 2 electrons also. So that's what oxygen's Lewis dot model would look like. Okay. And again, we're not going in order here. Notice I actually went back and I got hydrogen. So 1 energy level and only 1 electron. So we would call it H. And I'll put the first dot here on the right. Helium. Remember, helium's kind of the oddball. It's put here in group 18, but it doesn't really have the same number of outer electrons as the rest of them in group 18 because it only has 2 electrons. So we'll write He, put 2 dots on there. Make sure the dots are visible. Mine are prominent enough, I think you can see them. All right, and why don't you try the other 2? Just pause the video here. Try to write the Lewis dot symbols for those last 2, and then restart the video and see how you did. Okay, spoiler alert, if you haven't done this yet, you should pause it now, but I'm going to give you the answers to these last ones. So now we have 1 electron in the second energy level. So that's column 1, group 1, in the second energy level. So we're looking at lithium. So the symbol will be Li. I want to remind you, when you have double letter symbols, you have to make the second letter a lowercase letter, okay, not 2 capitals. And this one will just have 1 dot, kind of like the hydrogen, right? And then this one here is the element beryllium, Be, and it should have 2 dots somewhere. Again, I don't care if you have 1 on each side, but that's what those will look like, okay? All right, so that's our introduction to the Lewis dot symbols. Okay, now we'll start on our next page. So what's helpful about these dot symbols? First of all, they're much easier to draw, but they show you something important. They show you how close an atom is to having a full, and that's an important word, I capitalize it, a full outer energy level. Remember, sometimes we call that outer energy level the valence level. And when you read this in textbooks and maybe online, you might hear them called shells. I don't know if I've used the term shells or not. Sometimes I'll use the word shells as well. Okay? So why is that important? It turns out, down here, I wrote this in bold, that the most stable, or what I sometimes call happy atoms, are the ones whose outer energy level is full. Now remember what full means. For most atom, that means 8 outer electrons. Some of them can't hold that many, but full means 8 or maybe 2. And if you are very close to being full, you're going to want to try really hard to become a full outer energy level. And that makes that particular element very reactive. Reactive. They interact with other atoms very easily, almost to the point of sometimes causing an explosion. That's what chemical reactions are. Those are atoms that are trying to get electrons or to give away electrons so that they can have full outer energy levels. Okay? Okay, so let's use some examples from the previous page to show kind of how the Lewis dot models can help us see how close things are to a full outer energy level. So we'll just start with the first one that we had there. So boron, remember boron had 3 outer electrons. It's in group 13, and everything in group 13 has those 3 outer electrons. All right? So let me show you again what we're representing with this Lewis dot model. Okay? So there's 2 ways for boron to get a full outer energy level. One way would be to acquire 5 more electrons so that these 3 would then become 8 outer electrons. And remember, 8's the most. But there's another way, in fact, a better way for boron to do this. If boron were to lose its 3 electrons, then look what happens. The second level is no longer the outer energy level. The first level would be. And that level is already full if it has 2. So for boron, it's going to be more likely, more easy for it to lose 3 electrons than to try to get 5 more. Okay? So what we'll say about boron is it needs to lose 3 electrons. to have a full outer energy level. And in fact, anything that has 3 dots around it is going to be the same way, okay? Now I'm going to skip carbon because carbon is kind of right in the middle. So it's got 4, so it's got 2 choices. It can either try to get 4 more or get rid of those 4. It turns out it's not going to do either one. So we'll just skip that for now. But let's look at nitrogen. So nitrogen, with its 5 outer electrons, we show the Lewis dot symbol like that. And then I just want you to be able to look at this and say, okay, I'm trying to get 8. There's 2 ways to do it. I could get 3 more dots here, or I could get rid of 5. Always pick the easiest way. Nitrogen will gain 3 electrons in order to fill its second energy level, okay? And what about oxygen? Oxygen, if you look back at the previous page, started with 6. And so it is only 2 away. So it will gain 2 electrons. Now it turns out because oxygen is closer to having a full outer energy level, it's only 2 away, whereas nitrogen is 3 away, oxygen is more reactive. It's going to be out looking for other atoms that will give it 2 electrons. And that's what this is all about. Chemistry is all about the gaining and sharing and losing of electrons just to make every atom happy. All right, let's look at one we didn't do before. How about argon? So argon we didn't do, but we can find argon on the periodic table. It's right over here in group 18. In fact, it's also element 18. What does that tell you? It means it has 8 valence electrons or outer electrons. So we can draw 8 dots around it for its Lewis dot model. So when you see 8, I want you to think happy. So it's already happy, in quotes, of course. They don't have feelings. So it will not gain or lose. It doesn't want to give them away, and it doesn't want to acquire any more. Okay? All right, let's look at another one, the last one here. Sodium. I'm going to do a demonstration for you if you're in my class, and you'll see how reactive sodium is. So here's sodium way over here in group 1. That means it's got 1 outer electron, okay? What it really looks like, if you could see all of its electrons, it's right here. So it's got 2 in the first, it's got 8 in the second, and it's got 1 right there in the third. So think about the easiest way for sodium to become happy. It certainly is going to have a difficult time gaining 7 more to make 8. But if it gets rid of this last one right here, then the third energy level is no longer the outer level, but instead the second energy level is. And so it will lose that 1 electron. And once it does, it will have 8 outer electrons and it will be happy. So the ones that are so close, like sodium or anything here in group 17, because the ones with 7 outer electrons are also 1 little electron away from being happy. We're going to talk about those being very reactive. They will react with each other almost explosively sometimes. Okay? So pause it right here. If you need to go back and kind of catch this again, this is a really critical point that I'm going to make that's going to connect not only to this unit, but the next couple of units as well. So this is a pretty lengthy video, as you can see. So this is a good time to maybe take a break. Pause it here, take a little brain break, a little stretch, get a little drink of water, something like that. That helps the brain kind of refocus a little bit. A little bit of movement definitely helps. And then you can continue on with the last part. Okay, remember, you can always go back and watch this a little out of order, replay any parts that you need to. Okay, so on this last page, I'm going to go through group by group. And again, when I say group, I'm talking about the vertical columns on the periodic table. I'm going to just talk about some general properties of some of the elements, okay? So we're going to start with group 1. This includes hydrogen gas. It's the only gas on the metal side. So you think, well, why would you put hydrogen here? Shouldn't it be over here with the other gases? Well, no, because it has one outer electron. It really does belong with this group. And it has some other properties that are similar. So what we're going to see is properties of the elements have to do with how many outer electrons they have. So that's why these are all very similar to each other. Okay? So all the elements in group 1 have this for their Lewis dot model. There's a symbol. Now I'm going to use a generic symbol X, that just to take the place of what the element symbol would be. And they have one dot on there, okay? So because they are one electron away from having a full outer energy level, it makes them highly reactive. Even explosive elements. And that also means they are not found in element form. So what do I mean by that? So you can find a lot of these things, sodium, potassium, etc., but you're never going to find them as a single atom because they're so reactive, they'll find something else to react with to form what's called a molecule or a compound of multiple atoms that are all kind of joined together because they're trying to get each other's electrons. All right? So not found in element form. Some of you have heard of before, for example, sodium, important element that we take into our bodies, usually in the form of salt, sodium chloride. Sodium chloride is a compound that has sodium in it. Okay, we'll talk more about compounds in the next unit. All right? In group 2, the Lewis model would be a symbol with 2 dots on it. Okay, still reactive, but not as much. So less reactive than the group 1 atoms. And some of these group 2 elements, you'll recognize the names. In fact, these are probably some of the minerals that your body needs. For example, calcium and magnesium, 2 important minerals that you take in a lot of the foods that you eat, or maybe a multivitamin. Okay, so now groups 3 through 12. And I hope you remember from the last unit, this is a special group of elements. Actually, I should say it's 10 groups of elements. But that big chunk right there was the group that didn't follow the pattern of outer electrons. And I could show you their dot diagrams. Most of them have 1 or 2. But I do want you to know this. They are known as the transition metals, or sometimes called transition elements. So know that term. It's one of your vocabulary terms on your page. And there are a lot of, let's call moderately reactive metals. And there's a lot of them in there that you're familiar with. So here's iron. Iron is very easy to rust. You know, it sits out in oxygen, especially when it gets wet, and it'll rust. That's a chemical reaction. That's iron trying to get rid of a couple electrons. Cobalt, you may have heard of cobalt, a nice blue glass, cobalt glass. Nickel, copper, and zinc are pretty common. You're probably familiar with silver, gold, palladium, platinum, real common, real valuable. Tungsten used in the filaments of light bulbs. So these things are all over the place and real common. And so, there's not much to say about them. There's one interesting thing is that many form brightly colored compounds. Compounds is what we call it when you bond a metal with something else. I was talking about that trading of electrons. We get what's called a compound. So, for example, if you're an artist, you might use a color called titanium white. If you look at in the ingredients in white paint, white pigments, you might see that. Copper can have a nice greenish color to it. Cobalt, I mentioned blue cobalt glass. So lots of like bright reds of iron, that distinct color of clay. That red color is because of the iron in there. Okay, a lot of iron oxide, which is very red. All right. So moving on to 13 through 15. Not much to say about these, and that's because if you look at what we have here, every one of these groups includes some metals, some metalloids, and some nonmetals as well. Okay, so we got the nonmetals up here at the top, and then we got metals underneath. I should say that there's an exception. 13 is a little bit more metallic. But these don't have as many things in common with each other because we have kind of a variety. So each of these includes some metals, metalloids, and nonmetals. I'm not going to give their Lewis dot symbol because they would have either 3, 4, or 5. Okay? They don't readily, that means easily, gain or lose electrons. If I could just show you again what some of those look like. For example, nitrogen is in group 15. See how it's got 5? Well, that means it needs 3 more. Well, gaining 3 is actually kind of difficult. Okay? 2 is manageable. 3 is very difficult. Boron in group 13, also not very easy to lose 3. So when you got like 3 and 4 and 5 electrons to start with, you're just not going to do much gaining or losing. Okay? All right, group 16. This Lewis model would look like this. A symbol and then 6 dots around it. Again, the way I was trained, we put 2 on the right, 2 on another side, and then 1 on each of the other 2 remaining sides for a total of 6. Okay? And again, if you look at some of the elements, you're familiar. Oxygen, I mean, that's a gas that we breathe. Sulfur, you might not have seen sulfur before. It's a brightly colored powder. Okay? Selenium, that actually looks like a mineral. So it almost has a little metallic look to it, which is a little unusual because it is a non-metal. Okay? So a wide variety there. Not much to say about group 16. Again, oxygen is all over the place. Group 17. I do want you to know group 17 is known as the halogens. Okay? The dot symbol would have 7 dots around it. And now look, see how we're getting really close again to having a full outer energy level? These are, again, highly reactive. But these are all nonmetals. Okay, those nonmetals have a lot of outer electrons, so usually very close to having a full outer energy level. And some things you might recognize. Fluorine, that's the basis, the atom that's in fluoride, if you use fluoride in your toothpaste, hopefully. Chlorine, that's the other half of the salt that I talked about. Sodium and chlorine together make salt, sodium chloride. Bromine and iodine, again, probably ones you've heard before. All right. Interestingly enough, you might find some periodic tables that show this one down here. This is called astatine. Some characterize that as a metalloid. On my periodic table, I noted it as a non-metal. It's really not that important to know which is which. I'll never try to trick you on that. Okay, and then finally, group 18, known as the noble gases. And I want you to know why they're called the noble gases. I'm going to tell you this in just a second. So, helium, neon, argon, krypton, xenon. So the dot symbol shows 8 outer electrons. Now, what does that mean? It means it's already happy. And when you're already happy with a full outer energy level, running out of a little space here, so I just left off the word energy, that means it will not react with other atoms. Now, a little history lesson. Who were the nobility back in the day? The nobility. We still have some now, right? The kings and the queens and the princes and the dukes and all of the kind of high-level people. A lot of countries have done away with the nobility. I mean, once you moved out of a monarchy system, you didn't have too much of that. But the nobility were kind of known for keeping to themselves. They only hung around the other noble people, not the commoners, the regular people who lived in the towns. So because they didn't mix and interact, we've taken that idea and we've given the name to this group of elements that doesn't interact with other atoms. Isn't that interesting? So that's why they're called the noble gases. And they are all gases. Okay, and finally, now I'm sort of breaking the rule here. I said we were going to talk about groups, but I decided to talk about these two. These are not groups because they're a vertical column. They're groups just because they're a big chunk down here. 28 elements that are, remember, supposed to be squeezed in here between groups 2 and 3. But we don't have space on a piece of paper, so we put them down here. But they are known as, this upper set of 14 is called the lanthanides because the first element is called lanthanum. And actinium is the first in the second row called the actinides. Okay? So these are just 28, I guess, 28 metals of different kinds, some of them with very interesting names, and all very different. So I can't give you a dot symbol for these because they're all very different. But I will say these, their reactivity, how they interact with other atoms, is similar to the group 2 metals. So remember in group 2, they had 2 outer electrons. They were somewhat reactive, but not highly reactive. Many are used for different things. Here's something kind of interesting about them, especially the actinides. Many are radioactive, which makes them maybe useful, but also a little bit dangerous. So a couple of the ones you might recognize. Here's uranium. Yeah, that's the one that most people recognize. Uranium and plutonium, right? Kind of famous for the atomic bomb and other things like that, all right? So, all right, so I just wanted to give you kind of an overview, but the main thing I want you to see is that the number of outer electrons is a key indicator of what kind of reactivity you will get, okay? All right, so that's certainly long enough for now. That's plenty long enough. And I'll have you apply some of this, and we'll do some lab work and help you sink this stuff in a little bit better than just by watching me talk about it. All right, thanks.